Good evening, everyone. So, in the second lecture of ray optics, we'll be starting with the calculation of the focal length of spherical mirrors, right? So, in the last lecture, we discussed about the spherical mirrors, right? Now, we'll be calculating different quantities, right? Like focal length of a spherical mirror, mirror formula, image distance, object distance, and we'll be just also discussing the different rules of formation of image, right, at different places, right? So, let's begin with the focal length of a spherical mirror, right? Now, you can see here the spherical mirror we have taken for the calculation of the focal length of a spherical mirror is the concave mirror, right? So, this is the incident ray of light. A parallel beam or the parallel ray of light is incident on this concave mirror at point M, right? At point M. This is the incident ray of light. This is the incident ray. This is incident on this concave mirror at point A, strikes the mirror at point M, right? And this parallel beam of light or the parallel light will strike the mirror and it will follow the laws of reflection and it will pass through the point F, which is called as focus, right? This is the focus, right? And we know the focal length is nothing, it's a distance between the focus and the pole of a mirror, right? And that's what we call as the focal length. It means that the distance from F to P will be called as focal length, represented by small f, right? And distance from P to C is nothing, it's what we call as the radius of curvature, right? And C is the center of curvature, right? So if the angle of incidence is I, then the angle of reflection will also be equal to I, right? Because it will follow the laws of reflection. Now you can see here the normal is drawn for the spherical mirrors from the center of curvature, right? Because we know that radius is always perpendicular to the tangent in case of spheres, right? So normal will always be drawn from the center of curvature in case of spherical mirrors, right? So we have drawn a normal CM, right? Where the angle of incidence is I and angle of reflection is also equal to I, right? So there's a slight construction where drawing a perpendicular NF, right? On the reflected ray, this is the reflected ray. A perpendicular FN is drawn on this reflected ray. Now we can see there are two triangles. One is triangle CNF, another is triangle NMF, right? There are triangle CNF, and the triangle FNM, right? And both these triangles are similar to each other, right? They are similar to each other. Triangle FNM, right? FNM. So these are the two triangles which are similar to each other, right? So it means that if they are similar to each other, we know that C to M is the radius of curvature, right? CM is equal to R, right? This is CM, that's equal to radius of curvature, that's equal to R, right? That's equal to R. And so this is a similar triangle, so CN must be equal to NM, right? So CN here must be equal to NM, right? That's equal to R upon 2 because C to M is R, so Cn is equal to Nm, it must be equal to R upon 2, right? So the value of Cn is here half of the radius of curvature, right? Now let's focus on this triangle here, right? Triangle CNF, right? In triangle CNF, it's a right angle triangle, right? Right angle at N. The cos of angle of incidence I, right? You can see here if this line is parallel to the incident ray, right? If this angle is I, then this angle has to be equal to I, right? These angles we called as alternate angles, right? So this angle has to be equal to at C equal to I, right? So cos of I here will be based upon perpendicular for this triangle, right? So it will be Cn upon perpendicular CF, right? CF. Now the value of Cn is R upon 2, so it will be R upon 2 divided by CF. So from here, you can see here from here the value of CF is, the value of CF here will be equal to R upon 2 cos I, right? R upon 2 cos I. So this will be the value of CF, right? R upon 2 cos I will be the value of CF, right? Now, looking at this length, CP, right? C to P, or we can say the distance between the center of curvature and P is equal to CP, right? So it will also be equal to the radius of curvature, but we can write the Cp equal to this Cp will be equal to Cf plus Fp, right? It will be equal to Cf plus Fp, right? Fp. So the value of Fp will be nothing. It will be equal to Cp minus Cf. Cp minus Cf, right? Cp minus Cf. It will be equal to Cp minus Cf, right? Now the value of Cp is nothing. That's equal to R, right? It's the radius of curvature, and value of Cf is R upon 2 cos I, right? R upon 2 cos I. Now, using the paraxial approximation, for paraxial approximation, the incident rays of light are very close to the principal axis, right? If they are very close to the principal axis, then this angle of incidence, right? That's angle I will be very small, right? It will be very small. So we'll be using paraxial approximation here, right? So using the paraxial approximation, angle I will be small, right? Angle I will be small. If angle I is small, then cos of I will tend to equal to 1, right? So we can approximate cos I to 1, right? We can approximate to it to equal to 1, right? So FP is nothing, it's the distance between the focus and the pole of a mirror. That's what we call as the focal length. So this F is the focal length, right? So it will be R minus R upon 2 cos I. Cos I is 1. So it will be R minus R upon 2. That's equal to R upon 2, right? So you can see here the focal length of a concave or the convex mirror, right? Or the focal length of a spherical mirror with paraxial approximation is actually equal to half of the radius of curvature, right? It's half of the radius of curvature. So this is nothing. This is what we call as the focal length of a spherical mirror, right? This is the focal length. The focal length of a spherical mirror is nothing. It's half of its radius of curvature, right? This will be the same for convex mirror and the same for the concave mirror as well, right? You can see here these are the parallel rays, right, striking the mirror, and they will pass through the focus, right? Upon reflection, they will pass through the focus, and the distance between this focus and the pole is what we call as the focal length, or that's equal to half of the radius of curvature, right? Now, let's talk about the different rules for image formation, right? There are different rules, or we can say certain rules which are followed by the laws of reflection, right? Let's compile all these rules, right? So that we will be using for the formation of images, right? So the rule first is that if a ray of light, right, if a ray of light which is parallel to the principal axis, right, a ray of light which is parallel to the principal axis after reflection from the mirror, right, passes or appears to pass through its focus, right, passes or appears to pass through its focus, right. It means that if we have a ray of light which is incident, right, which is incident parallel to the principal axis, right, it will pass through the focus after reflection, right? Or in other words, we can say that if a ray of light passes through the focus, then it will appear to be parallel to the principal axis after reflection, right? So it will also follow the laws of reflection, and the normal will be drawn from the center of curvature of this spherical mirror, right? So the rule is that if a ray of light is parallel to the principal axis after reflection, it will pass through the focus. Or if a ray of light is passing through the focus after reflection, it will pass parallel to the principal axis, right? It will pass parallel to the principal axis. And the image form, talking about the image formation, we know that image is a point of intersection of the reflected or the refracted rays, right? That's the image point. Now, after reflection, the parallel rays will meet at infinity, or we can say the image will be formed at infinity, right? Now, if the object is at infinity, it means the rays will be coming parallel from the object, right? It will be parallel to the principal axis, right? After reflection, they will pass through the focus, or we can say the image will be formed at focus. So this is the first rule. Parallel rays will be passing through the focus, or the rays passing through the focus will pass parallel to the principal axis after reflection, right? Now, let's talk about the second rule. The rule second is that a ray passing through or directed towards the center of curvature, right? So it means that if a ray is passing through or is directed to pass through the center of curvature, right? And we know that when a ray of light will pass through, when a ray of light will pass through or appears to pass through center of curvature, right? Then at the point of incidence on the spherical mirror, the angle of incidence will be equal to angle of reflection, right? And the normal will be drawn from the center of curvature, right? So if a normal will be drawn from the center of curvature, it means that the normal will actually coincide with the incident ray as well as reflected ray. Or we can say the angle of incidence will be equal to 0 and angle of reflection will also be equal to 0. That's the reason this ray will pass, or it will retrace its path, right, and will pass through the center of curvature after reflection, and the image formation will take place at the center of curvature itself, right? So the rule is that if a ray passing through or directed towards center of is directed towards the center of curvature, right, it will always retrace its path, right, following the laws of reflection, right, and the image will be formed at center of curvature itself, right. Then the third rule is that if the incident and reflected rays at the is actually incident at the pole of a mirror, right, and once again they will follow the laws of reflection, they will pass symmetrically or they will reflect symmetrically from the pole of this mirror, right? Or we can say here once again the laws of reflection will be followed. Angle I will be equal to angle R, right? So this is how the laws of reflection will follow in case the incident ray is striking on the pole of a spherical mirror, right? And the rays after reflection will be a diverging rays, right? There will be a diverging rays. So these rays will be diverging rays after reflection, right? So in reflected ray will diverge as compared to the incident ray, right? And there will be image formation at some point. We will see that later on how the image will be formed after reflection in different cases, right? So these are certain rules with the help of which we can actually see how the image is formed, right? But let's talk about the image formation by concave mirror. Now we can see if we place an object at infinity, right? We have seen that if the object is placed at infinity, right? And then the rays will be coming parallel from the infinity, right? After the rays coming parallel from the infinity, they will strike at some point on the spherical mirror and they have to pass through the focus, or we can say the image will be formed at focus, right? Image will be formed at focus, and the image formation will take place. Actually, the rays after reflection will actually meet at the focus, so the image formed will be real, and the rays will actually meet below the principal axis, right? And therefore, we can say the image formed will be inverted, right? It will be inverted. It will not be upright image. It will be inverted image, right? And it will be highly small, or we can say it will be highly diminished, right? When the rays of light are coming from the infinity, the image formed will be highly diminished, right? It will be very small image, right? Now the second case is that if the object is placed in between infinity and if the object is placed in between infinity and c is the center of curvature, right? Now in that case the image will be formed between the center of curvature and the focus, right, following the laws of reflection, right? Once again the image will be formed will be real image, and it will be inverted image formed below the principal axis, right? It will be formed below the principal axis, right? It will be a real image, it will be formed below the principal axis, right? So this is the second case of formation of image, right? If the object is between infinity and center of curvature, image will be found between focus and center of curvature, right? It will be real image and inverted in nature, right? Now let's talk about the third case, right? The third case of formation of image. Now you can see here the object is placed at C, or the center of curvature. We know that when object is placed at the center of curvature, right? The rays coming from the center of curvature will actually pass through the center of curvature, right? Will actually pass through the center of curvature, right? And after reflecting from the center of curvature, they will meet at the center of curvature, right? The image will be formed at the center of curvature, and the image formed will be real image and inverted, right? And the height of the image will be equal to the height of object, or we can say the image formed will be in equal size with the object, right? So this is the third case, right? And the fourth case is that if we place an object in between focus and center of curvature, right? In focus and center of curvature, right? The image will be formed beyond the C, right? The image will be formed beyond the center of curvature, right? You can see here the image I is formed beyond the center of curvature, right? Following the laws of reflection or rules of image formation, right? And the object or the image formed for this object will be enlarged image, right? It will be, its height will be greater than the height of object. That's why we say that it's enlarged image, and it will be inverted, right? It means that head of this image will be head of the object will be in the downward direction, and we can say the foot of this image will be in on the principal axis, right? Now, talking about this case, when the object in case of concave mirror is placed between focus and pole, right, near to F, right, very near to F, right. Now, in this case, the image is formed at the infinity, right? Image formed is at infinity, right? And this image formed will be actually virtual, right, erect and highly enlarged, because here in this case the reflected rays will be diverging in nature, right? Reflected rays will be diverging in nature, and they will not meet at any point in minus infinity, right? In minus infinity they will not meet at any point, right? But if we extend these reflected rays in the backward direction, they will definitely meet at some point, right? At some point, and the image formed will be virtual, right? And it will be upright or erect, right? And it will be highly enlarged image, right? So this is the image formation in case of concave mirror, right? These images are formed using the what we call as rules of image formation, right? There are certain rules with the help of which we can actually form the image, right? We can use those rules to form the image for different positions of the object, right? Now, before discussing the magnification or before discussing the mirror formula, right? It's important to know about certain convention, right? It's very important to know about the certain conventions that we use in case of spherical mirrors, right? And these conventions we call as sign conventions for spherical mirrors, right? Now, the conventions are that, right? You can see here we have a spherical mirror here placed in this diagram, right? We have shown this is the direction of the incident ray, right? This is the direction of the incident ray, right? So these are different distances, right? Now we'll see how actually we can use these conventions, right? For different image formations, right? For different image formation. So the first convention is that object is placed above the principal axis, right? The first convention is that object is placed object is placed above the principal axis, right? The object is placed above the principal axis, right? And the second convention is that all distances are measured from the pole of a mirror, right? All distances are measured from the pole of a mirror. So all distance in case of concave mirror as well as in case of convex mirror, the distances will be measured from the pole, right? All distance are measured from pole of a mirror. And the third point is that distances measured above the principal axis will be taken as positive, and the distances measured below the principal axis will be taken as positive, right? So distance measured above the principal axis, distance measured above the principal axis will be taken as positive, right? And distances measured below the principal axis will be taken as negative, right? And distances measured below the principal axis will be taken as negative. It will be taken as negative. So this is the point number third. The point number third is that distances measured above the principal axis will be taken as positive, and the distances measured below the principal axis will be taken as negative, right? It means that if we place an object at this place, right, then the height of this object will be taken as positive, right? And let's suppose the image is formed, inverted image is formed, right? If we measure the image, height of image, now this height of image will be taken as negative, right? Because this image is formed below the principal axis, right? You can see here height of object is taken as positive and the height of image is taken as negative because height of object is above the principal axis and the height of image is below the principal axis, right? And the fourth point is that distances measured along the direction of incident light is positive, right? Distance along the direction of incident light is positive. Along the direction of incident light is positive, right? And distance opposite the direction of opposite the direction of light is taken negative, right? So these are certain conventions, right? These conventions will be followed, right, in the formation of image, right? And to comment on different nature of the image, right? So the distance is measured along the incident, along the direction of incident light is taken as positive, and distance opposite the direction of light is taken as negative, right? So these are certain conventions, right? You can see here, this is the direction of the incident ray of light, right? Now we can see, you can see that if we place object here, the object distance will be measured from the pole to the object, right? It will be opposite to the direction of incident ray, so it will be taken as negative. And if image is formed here at this position, right? Let's suppose this is the image point, then this image will be measured from the principal axis, right, along the direction of incident ray of light. This image will be taken as positive, right? So these are the four conventions which are very important in deciding the nature of the image formed, right? Now let's discuss about let's try to solve or let's try to derive the what we call as mirror formula, right? It's a relation between image distance, object distance, and the focal length. That formula we call as mirror formula, right? We call that formula as mirror formula, right? Now let's try to measure this one by one, right? Now let's see here, you can see this is the incident ray of light and this is the reflected ray of light. Now let's suppose the angle of incidence here is theta, right? Then this angle of reflection will also be theta here, right? Because angle of incidence has to be equal to angle of reflection, right? This is the object here, right? Who is the object here, right? This is the image point. Now you can see here, let's suppose this angle here is alpha and this angle here is beta and this angle here is gamma, right? This angle is alpha, this is beta and this is gamma, right? Now, talking about the paraxial approximation, we know that in case of paraxial approximations, in case of paraxial approximations, paraxial approximation, once again we'll be using paraxial approximation here, right? The tan of theta, since theta is small, tan of theta will be taken as theta, right? And sine of theta will also be taken as theta, right? In case of paraxial approximations, right? Now we can see here, if we calculate the value of alpha, right? If we calculate the value of alpha here, we'll be using tan of theta, right? Tan of theta or tan of alpha. So tan of alpha will be MP, right? It will be equal to MP upon OP, right? That's the object distance. MP upon OP. And the value of beta will be equal to MP upon PC, right? Will be MP upon PC. And the value of gamma will be equal to MP upon PI, right? MP upon PI. This will be the value of gamma, right? Now you can see in triangle, OMC, right? In triangle OMC, there is an exterior angle beta, right? There is an exterior angle beta, and we know that in case of triangle, the exterior angle is actually equal to the sum of two interior opposite angles, right? Sum of two interior opposite angles, or we can say that the beta will be equal to alpha plus theta, right? Alpha plus theta, and the beta is equal to alpha plus theta, and the value of gamma will be equal to beta plus theta, right? Beta plus theta, beta plus theta, right? This will be the value of gamma, right? This will be the value of gamma. Now from here, theta will be equal to beta minus alpha, or theta will be equal to gamma minus beta, right? Gamma minus beta. Since theta is beta minus alpha and theta is gamma minus beta, it means beta minus alpha has to be equal to gamma minus beta, right? Gamma minus beta. Or from here, we can see here twice beta will be equal to alpha plus gamma, right? Alpha plus gamma. That will be twice beta, right? Now talking about the value of beta, right? The beta, we know that beta is equal to MP upon PC, right? Beta is MP upon PC. That's equal to value MP, right? Now you can see MP in this diagram from here to here, this perpendicular distance is the MP, right? PC is the distance between center of curvature and pole, right? That's nothing, that's equal to the radius, right? Or we can write beta equal to MP upon R, right? MP upon R. Similarly, the alpha will be equal to MP upon OP, right? OP has the value equal to the object distance, right? Because O to P is the distance between the object and pole of this mirror. We call this as object distance U, right? So alpha will be equal to MP upon U, right? MP upon U. And the value of gamma, that will be equal to MP upon PI, right? MP upon PI. PI is nothing, it's the distance between the image point and the pole of a mirror. That will be nothing, that's the image distance P, right? Image distance P. Now we can substitute the value of beta, alpha, and gamma in this relation, right? In this relation, we'll substitute the value of beta, alpha, and gamma, right? In this relation. Now it will be twice beta, right? It will be twice beta, that's MP upon R, right? MP upon R. Equal to alpha, that's MP upon U, right? Plus gamma, that's MP upon V, right? MP upon V. Now from here, MP, and MP will get cancelled. We're left with the relation 2 upon R, right? That's equal to 1 upon U plus 1 upon V, right? This formula we call it as mirror formula, right? This is nothing, this is the mirror formula for spherical mirror, right? This equation we call it as mirror formula, right? And it's only applicable in case of paraxial approximations, right? It's only applicable in case of paraxial approximations. It means that incident rays of light should be very close to the principal axis so that this angle theta will be very small. Then only we can use this formula for the calculation of different values of object, right? We can calculate the object distance, we can calculate the image distance, right? Or any of the physical quantity, right? That's mentioned here, right? So it will be 2 upon R is equal to 1 upon U plus 1 upon V. We know that R upon 2 is focal length, right? If we substitute the value of R upon 2 equal to F, right? We'll get the mirror formula as 1 upon F. That will be equal to 1 upon U plus 1 upon V, right? So this is nothing, this is the mirror formula, right? Or we can say that the final equation But the mirror formula will be here equal to 1 upon f is equal to 1 upon u plus 1 upon v, right? This is the mirror formula. So this formula can be used to calculate the nature of the image, right? Can be used to calculate the nature of image for different object positions, right? It can be used to calculate the nature of image for different object positions. Now you can see here, let's suppose if we place an object, at infinity, right? If we place an object at infinity, let's suppose u is infinity, right? U is infinity. Then 1 upon f is equal to 1 upon infinity, right? And because the object is placed in front of the mirror, right, in front of the spherical mirror, or we can say that the direction of the image distance will be negative because it will be opposite to the direction of the incident ray of light from the pole. We can take it as 1 upon infinity with a negative sign, right? It will be 1 upon v, right? So this term will be 0, right? That will be equal to 1 upon v. So we can also confirm from here, from this equation, that image will be formed at the focus of a mirror, right? Image will be actually formed at the focus, or the image distance will be equal to focal length, right? So we can see here, when a parallel beam of light, right, strikes the spherical mirror, it will always pass through the focus, right? It will pass through the focus and the image will be formed at the focus, and the focal length will be equal to the image distance, right? Focal length will be equal to the image distance, right? Now similarly, if we keep the object at focus, right, it means the u is equal to f, right? U is equal to f, or we can write it as minus f, right? Because in this case, you can see here, if u is equal to minus f, then object distance has to be equal to negative, right? Because it will be placed in front of the spherical mirror, and this distance will be measured opposite to the direction of incident ray of light, right? Now we can use this equation. The focal length will also be a negative. Let's suppose this is a concave mirror. The f will also be taken as negative. We can use this equation 1 upon f. That will be equal to 1 upon u plus 1 upon v, right? Now substituting the value of u equal to minus 1 upon f. Focal length is also negative, so it will be minus 1 upon f. Minus 1 upon f, right? Plus 1 upon v, right? So from here you can see the value of v will become infinity, right? It means the object will be formed at infinity, right? It will be formed at infinity or infinite distance from the pole of a mirror, right? So we can confirm all the rules or all the image formation from this mirror formula as well, right? Substituting the different values of the object distance, right? Or we can say that the nature of image formed from at different positions of the object can be actually verified from the mirror formula as well, right? Now let's talk about the magnification, right? Magnification. So magnification is nothing. It's the relation between the image distance and the object distance, or it's the relation between the size of object and the size of image, right? Size of object and the size of image. Or we can say it gives us the relative idea between the size of object and the size of image, right? So magnification is nothing. It's defined as the magnification M is nothing. It's the size of image upon size of object, right? Size of image upon size of object. Size of image upon size of object, or we can say it height of image upon height of object, right? Height of image upon height of object. So this is how we define the magnification, right? Now you can see here, we have an object, right? We have an object here in this diagram of height h, right? The rays of light, incident rays of light strikes the pole of this mirror and will get reflected back symmetrically, right? And at some point here, the reflected rays meet at some point and image is formed, right? Image is formed. Let's suppose the image height of this image is hi, right? Height of this image is hi. Now from here you can see here, angle of incidence is theta, angle of reflection has to be theta, right? So this tan of theta can be written as height of object upon object distance, right? And similarly, tan of theta can be written here as height of image upon the image distance, right? V, right? Now from here, height of object upon object distance will be equal to height of image upon image distance, right? Or we can write V upon U equal to H, height of image upon height of object, right? So this is the magnification, right? This is the magnification in case of spherical mirrors, right? Now you can see here the image, the height of object is above the principal axis, right? It will be taken as positive, right? And the height of object, height of image will be height of image is below the principal axis, right? It will be taken as positive, negative, right? So we have to take value of hi here equal to minus hi, right? Using sign convention, right? Using conventions. Using sign convention, we have to take this distance hi as minus hi, right? Now this hi upon height of object, this is the magnification, right? This is the magnification and it will be equal to minus v upon u, right? This will be equal to minus v upon u. So this is the magnification in terms of image distance and object distance, and this is the magnification in terms of height of object and height of image, right? So this is also the magnification, right? So we can calculate magnification either by calculating the height of image and height of object, or we can calculate the magnification by calculating the image distance, right, upon the object distance, right? Now you can see here, in case of spherical mirrors, right, the image, the real image will be formed in front of the mirror, right, and the virtual image will be formed behind the mirror, right? It will be formed behind the mirror, or we can say here, both the object distance and the image distance in case of a real image, it will be negative, and overall the magnification will be negative, right? That means that if the magnification comes out to be negative, right, we can say that image formed will be real. Image formed will be real, right? And if magnification is positive, right, then the image formed will be virtual. Then the image is virtual. Then the image is virtual. So concluding all the three equations, right? The focal length is half of the radius of curvature, right? In case of spherical mirrors. And we have this equation 1 upon focal length, that is equal to 1 upon u plus 1 upon v, right? That's the mirror formula. And finally, we have the magnification, that's m, that's either equal to height of object, height of image upon height of object, and that will be equal to minus v upon u, right? So actually, magnification tells us about the nature of image, right? Magnification tells us about the nature of image formed, right? The magnification tells us about the nature of image formed, right, at different positions, right? So using these three equations, we can actually conclude about the anything about the spherical mirrors, right? In the next lecture, we'll be starting with the refraction, right? We'll be dealing with the refraction. In the next lecture tomorrow, we'll stop here. Till then, take care and goodbye.